Hey guys, well here we are back again with hopefully a solution to the cooling problem. So I'm just going to quickly show you, you should have already seen the other video, but I'll go ahead and show you the changes that I've made to this intake, and then we're going to go out, run it, test it, and have a good look. So the only changes I have made is all down here. Now, compared to what I started with, that run that we did previously, this intake diameter has been reduced even more. So I've actually come down a little bit smaller this way, more importantly, a little bit further down on top. And yes, there's sticky tape absolutely everywhere. I've gone ahead and just sealed up all of the inside, but the important bit is before, I'm trying to hold the camera so you can see, is there was no actual ramp here. Is after this lip, it would kind of just go straight up. And so you can kind of see there, I can push up. So what I'm doing here is really just smoothing out this intake here. And the overall design with really any intake is a smaller hole going into a converging duct, a diverging duct. And what that means then, Bernoulli's theorem, is we'll slow the air down and increase the pressure on the front. So the way this cowl was before, this intake, is the opening here was actually bigger than what's at the radiator. Really bad design, really bad design, where basically you have a converging duct, which increases the velocity, decreases the pressure. So if there's a lower pressure in against the front of the radiators, well, it's never going to exit out through that cowl flap. So we're trying to recover some pressure onto this intake, but also smooth this ramp here, because what was happening is air was flowing in, hitting the radiator, flipping back around and coming straight out over the top, over this lip that wasn't there. So what I've done to combat that is, you can see it from the side here, is this lip is now angled forward quite a bit, and it now has a radius. So I've got a ramp here that should make it exceedingly difficult for any airflow to come back up and come forward, because now the air has to come forward a very long way. I'm still retaining all of the lines that were designed into the aircraft, which, you know, for better or worse, we don't know whether they're actually useful or not. But this should help, and probably the correct aerodynamic design, it would be slightly different to what I have. So you can see how I've got the major, or the tighter radius up top here, and then sort of like a longer radius there. Well, fundamentally, the better design would be to have that steeper radius here, so it kind of went down and around like that. However, this looks somewhat aesthetic with the actual cowl, and I don't want to rebuild the whole cowl. So this, I think, is going to be a compromise, but it is going to help in flight. High angles of attack, imagine the aircraft flying along at a high angle of attack, is the relative airflow is now going to be coming up at a bit of an angle like this, and it's going to make sure at low airspeed that this intake is indeed getting a great big mouthful of air. Whereas if it was the other way around and that radius was further down here, there would be more air spilling over the top of the lip and then following that channel down, or being blown up over the top of the cowl. So fundamentally, it would be a slightly better design, but I think this, what I have here, is a good series of compromises, and it would be relatively easy to retrofit this to the cowl without sticky tape and everything. I will maybe talk about how that works, how I'm planning on doing it later. I need to go test it first. The only other check I really needed to do was the distance between there and the prop. This is a variable pitch propeller, so the blades do change, but I've gone ahead and put the blades here at full course pitch, and you can see there's still quite a lot of gap there. But now that middle part of the blade here, it's hopefully going to be sending a lot more air directly into this intake. So I'm really confident. Well, not really confident. I'm quite confident that this is going to really help. And so you can see when it's running on the ground is I've got tufts everywhere. So I've got tufts on the lower lip. I've got 3 on the top. And what we were seeing when we were ground running it before is these tufts, you can see there, they're actually taped backwards. So what the relative airflow should be doing. What we were seeing when we were ground running it was these tufts were actually coming up over the top of this lip, and all of that cooling air was just escaping up over the top. So I've added a few more tufts so we can have a slightly better look at what the flow is doing. I haven't removed or added any for this exit yet. I think it's kind of redundant because I believe the actual problem is right up here. So how I got those radiuses is there's literally just some silicone hose, and I've just taped the silicone hose onto the actual cowl. But just even fundamentally seeing how that intake is kind of raked forward just slightly. It's only a small change, but small changes should have, I think this small change will have a really large effect. So I'll go ahead and test it now, do some ground runs, and the temperature outside today isn't conducive really for proper temperature testing. It's kind of overcast. I did a little bit of math on it. So the density altitude is currently about 800 feet. Outside air temperature is 20 degrees, 73% humidity. So we've got a fairly dense amount of air, but I'll talk about it in the cockpit. Everything that I've measured so far when I've ground run this is the only time the temperatures have been stable is when there's no cowls on the aircraft. Every other time I've shut the aircraft down to the 105 to 110 degrees Celsius. So if making this little change, I'll be able to tell in the cockpit if I'm going in the right direction, and then I'll be able to review the footage and we'll be able to see but if there is any change. But so it's not a true high temperature test, but having some flow through the radiator is going to be better than the almost zero flow that we've had so far. So I'm going to go get the aircraft dragged outside, chock it up, and set the camera up, and hopefully we're going to see some answers. For you guys, you're going to see it right now. Okay, so I've got the aircraft here started up, warmed up, and now just moving into adding some power. You can see from the outside there what the tufts are doing. They're looking pretty reasonable, and if anything, they actually look like it's actually getting a little bit more air into that. Oh my god, what a seamless transition. A little bit more air into that upper intake. Now, what we really care about is having a look at those tufts on the inside of the intake there. The inlet for the radiator. Interestingly, you can kind of see that little dangling tuft there. It's kind of pulsing going in and out, but it's not rolling up over the top of that lip. Why that's interesting is tuft testing, it kind of shows, it's designed to show you the flow, right? The boundary layer, what is happening to the airflow really close to a surface. But if you look closely and you understand what the tufts are telling you, they will also tell you pressure. They will also tell you pressure. So the tuft, this is my opinion, obviously I'm not sitting in front of a CFD, I'm sitting in front of a computer on a boat, that tuft that you can see right in the middle of the screen there, how it's oscillating backwards and forwards, that tuft is telling me that there is positive airflow now flowing through that intake. However, the pressure is oscillating. So basically, the pressure is building up inside that intake until it gets to a point that it relieves, which means it's flowing through the radiators, and then the pressure builds up. Now, initially, I thought it was in time with the propeller, but if you
if you look closely at each time the propeller passes in front, it's not in tune with the impulse of the actual propeller blades. So I did think that. I was like, oh, okay, I'm just watching the airflow as each blade passes through the intake, but it's actually the lower frequency than the propeller is rotating at. The other interesting thing to look at here is we're definitely going in the right direction. We're definitely going in the right direction because now there definitely isn't any flow coming back up out of that lip. However, the pressure because the pressure is coming in these waves, the cooling isn't as efficient as maybe it could be. But what I was trying to say is the interesting bit is have a look at all of the tufts around the undercowl cooling intake there. They actually look like, just with this small little lip that's been added, is they actually look like that they're drawing a little bit more air. There looks like there's a little bit more flow compared to the previous video that's on the channel. It looks like there's a lot more flow going into that cowl inlet that's there. Which is also helping with cooling. So just this lip, it looks like it's actually helped get a little bit more air into that cowling, and also has given me some cooling. And I ran the aircraft. I could see right away with how the temperature increased, just sitting there idling and adding power. I could see that the temperature increase of the engine was far slower than what it was previously. So from this, I could gather, even before I looked at the data, I'm starting to head in the right direction. The outside air temperature condition and everything was similar compared to the first run. So I can see this, and I was starting to feel quite positive. So I did move on from this, and you'll see here soon is I did actually decide, as I said at the start of this video, I actually ended up putting the extra bit of hose in place, but I'll save that for the next part of the video.
Okay, so after testing with the radius in the higher position, I've gone ahead and it still wasn't quite where I wanted it after reviewing that footage. So you can kind of see now what I meant by where the sharper radius where I wanted it is. Now I've got more of a ramp up here and the tighter radius is on the intake. So I've gone ahead, done that, added this radius lower. We've got some more tufts on the inside. We've got the 3 on the inside there, 3 on the bottom. I think there's 3 on the bottom. Oh no, I removed the 1 on the inside. So I'm going to go and give the aircraft a run like this, with this slightly smaller intake and that radius being a little bit lower. I'm going to do a full power run. It's the last run that I'm waiting for to get the plane ready to go. And hopefully today, it'll be a different video for you guys, but it should fly today. The plan currently is we'll test fly the aircraft in this configuration with sticky tape all over the front. Do an initial test flight just to see if this creates any weird cooling issues in flight. If it doesn't, we might do a second longer flight to really test the cooling system. But I think we're only going to need one more flight. You can kind of see there from the side how much further that intake sticks out, and it is relatively close to the prop, but when you actually get the prop in its lowered position, you can see that there's well and truly enough clearance. This lip, there's a lot. The only thing we might see is a little bit of accelerated wear. Just from that prop blast, there'll be a little bit of, what do you call it, degradation. It'll just, the air blast hitting here could potentially wear it away. Erosion. There we go, figured out the word eventually, erosion. So, pretty excited to see this run as is. Oh, and the other thing I'm doing is I needed some more temperature metrics. So I've got a probe down on the intake. I've got a probe here in the cylinders, you can kind of see it there, and I've got a little gauge here in the cockpit. And if you're wondering what the little gauge is, it absolutely is a barbecue temperature meter. It's the cheapest multiple probe temperature reader I could get, but it even has Bluetooth. So it's going to show me it's going to show me graphs and all this stuff. So the $50 barbecue temperature probe, it's got Bluetooth to my phone. It'll give me temperature graphs. It'll give me all of this stuff. It'll read up to, I think, 380 degrees Celsius. I only need to read up to about 200. Wonderful. We might even fly it with it on just to have a look at it and see what it works like. So the next ground runs are going to be a little intense. I'll try and record some footage on the inside, show you guys some of the failure testing, but because I'll be pulling a lot of power, temperature is going to be an issue, and yeah, obviously listening for loud sounds that shouldn't be there. So while this indeed does look dodgy as hell, before it does fly, I might actually put some extra tape over it. Might need to redo weight and balance, but I might just put a little bit more tape just to smoothen this area out. But I'll put some aluminium fiberglass reinforced tape on it, so it's a little bit stronger. And we'll remove all of the tufts, and it'll fly like that. So yeah, just another look at sort of what that intake now looks like. When it's actually modified completely, these corners will obviously not have as much of a drop off that you see there. They'll be nice and fared in. But yeah, I'll put the cows on, go make some engine noise, and hopefully this will look pretty good.
Alright, so let's have a look at this guy. Let's see what this thing looks like. So in this power run, like I said, I did do a lot of power. I'm not going to put the video of doing the internal cockpit view in this video. This is interesting enough as is, and the power setting that the aircraft's sitting at right now is even lower than the power settings before, so meaning there's less airflow. I'm going to let the video play out here for a little while as I talk through it, because I do pull nearly full power a little later, but hopefully the video will get to there. We can see that one tuff that's directly in the center line right in the middle. That pulsing that was happening in the previous video, which was the pressure building up inside the intake until the pressure was high enough to overcome the resistance of the radiators. Now when we can see, even at this lower power, which is at about 2500 RPM, previously it was at 3000 RPM, that little tuff there is pinned straight back. Not quite straight back, there's still some complex turbulence going on inside that intake, but for us, does the engine run cooler? Yeah, it does. It ran significantly cooler. Okay, so I've just snuck in this in post here. I just wanted to show a comparison between what I started with on the left and what it currently is. The first thing to notice is how much smaller the intake actually is. It feels counterintuitive, right? I need more air to cool, or I need more cooling, I need more air. But in fact here I've made the intake so much smaller, and yet I'm getting such a more efficient cooling, and that it's all due to the air literally spilling out the top. So again, just be directed to the top of that lip of the intake there. Those tufts are literally pointing the wrong way, even the one in the corner, compared to now where the tufts are actually forcing the air through the radiators. This is all due to pressure recovery and a better designed intake. And one came from the factory on the left, one came from the guy working at home. The interesting thing to look at here, I spoke in the previous video, only touched on it, where I talked about the low pressure and all of the inefficiencies behind a propeller spinner and that spinner to cowl sort of gap. If you have a real close look at the two tufts that are as close, that are the closest to the propeller, you'll see occasionally they actually get drawn in between where the spinner and the cowling is. And it's just showing where this air is going from, and just pointing out you can physically see where this inefficiency is between the cowling and the propeller. What's going on back there? I don't know, a whole heap of super duper complex aerodynamics, the spinny thing, high pressure. I don't actually know. It's just you read a textbook. The textbook says there's inefficiencies and there's a whole heap of losses between the spinner and the cowl. What's actually happening back there, it's beyond the scope of what I'm aware of. Fundamentally, I mean, I can tell you, yeah, there's a low pressure there, that's why it's getting sucked in. But why is there a low pressure behind a fixed spinning disc that doesn't have blades? No, I'm not there. I don't know. It'd be interesting to find out. If anyone knows, yeah, please let me know, because I'd super love to know the actual mechanism that is causing the air to get drawn in behind the spinner. It could be something, actually just spitballing here, it could be something like, I don't even want to, no, I'll spitball, why not? It could be something like the centripetal force of the spinner is drawing air into the gaps around the spinner and the blade roots. So there could be air going, the air's getting flung out inside the spinner. The spinner needs that air recovered, and maybe the air's coming in the backside of the spinner and then coming out by the blades. I don't know. I'm just sort of guessing here. I'm sure there's somewhere in a textbook. I just haven't seen it. Well, anyway, I've been rambling on. You hopefully been watching his little tufty boys flapping around there. It's interesting, you can see now I've pulled more power. That one little tuft that, there we go, the power's coming back now. That one little tuft that's in that little part of the cheek there that wants to point the exact wrong direction. You can see the little bit more power, that low pressure area does go away, and now the tuft is, well, it was pointing in the right direction, but as the power does come back, you'll see it does flick back. So there's something complex going on there. It's beyond what I need to fix for this aircraft. The only thing I care about is what's going on inside that intake. I do care what's going on around the outside, because putting that lip in the way I have, it could create turbulence downstream of that lip, which would affect the cooling air that goes under the cowling. And so this is really just to confirm that. But if anything, putting this lip on, I think it's slightly increased the amount of flow that's going into those two intakes either side of the spinner there. There's just the tufts, they seem to point a little bit more towards the intake, which means that that intake there is drawing in quite substantial amounts of air. I'm really happy with that. I wasn't expecting the lip to really help with the flow downstream to help direct it there. It would have been nice, but yeah, there it is. So that's an unintended consequence of the correct design. So I should have stuck with my instinct, right at the start of the video when I was doing the walk around over the design of that lip for the intake. I even pointed out, I'm like, the more fundamentally correct aerodynamic design is what you're seeing now, and I didn't go directly to that. I kind of iterated up to it, which is, again, it's okay, but I could have been a little bit smarter about it and gone, you know what, this is just what it should be. I should have listened to my instincts, but it's okay. Oh yeah, right now, have a look at the spinner there. Yeah, have a look at the spinner. Look at those tufts. They're getting drawn directly under the spinner. Weird stuff's going on back there. There's not much beyond the scope of what I'm trying to fix with this plane, but it is interesting to see those tufts are getting drawn almost directly under that spinner. Large inefficient loss there, but really, really happy with this. So the aircraft has flown since then. It flew this afternoon, and nothing fell off. However, oh boy, do I have a video for you guys. I set my phone up. The owner wanted to fly the aeroplane, even though I'm a test pilot, and I'm like a test pilot for RAOs, Recreational Aviation Australia. I've tested many aircraft for RAOs and manufacturers now in Australia. But the owner was very adamant that he would like to fly it. And Spoiler alert, he nearly crashed his perfectly good aeroplane. And if I didn't have a video in the cockpit, you wouldn't believe. You wouldn't believe me. And neither will the owner. I haven't had a chance to sit down with him and review the footage with him, but he's going to get a proverbial slap across the back of the head for being a trash pilot. And nearly crashing his plane. He doesn't know it yet, but his engine actually completely shut down, and he landed the plane safely. Everything's okay, but he doesn't know that he had a unintended in-flight shutdown of the engine due to pilot skill, or lack. I'll be generous. Let's just say lack of familiarity with the aeroplane. But then I'm going to go back to lack of not even skill, just core fundamentals of flying. It's going to be a very interesting video to show you. I hope you'll like that video. So it's going to come up real soon. Just tomorrow. I just wanted to finish off this footage now, and then tomorrow I'm going to go give him a smack over the head and show him how close he was to crashing a perfectly good aeroplane. And I get to defend myself because, he came back saying the engine ran rough and did all of these things. And, I'm the guy that's just spent all this time working on it. And if I did not have my camera in that aeroplane, the crosshairs would have been on me. That's the problem. But the crosshairs, after reviewing the footage of him nearly crashing his perfectly good aeroplane, they're the problems between the ears and the stick. It's pretty bad. It's really, really, really bad. Anyway, I'll leave you with that cliffhanger, and I hope you enjoyed the whiskers on this aeroplane tufting around. Talk to you soon.